Okay, welcome to the 12th and final lecture of Computer Architectures. This is our last meeting together. I hope you've enjoyed everything so far. In the module as a whole, we've covered the story of computer architecture. We started in the Stone Age. We went through the Mechanical Age, via the electromechanical age into the electrical age. When you take that kind of perspective on history, it puts you in a nice position to see where this is going and what might happen next. We call this studying the arc of history. When you study the arc of history, you can try to project it into the future. So today's lecture is going to be looking at what computer scientists are doing today that is preparing us for that future. You don't come to university to learn this year's trendy programming language. You come here to learn what computer scientists are researching now so that throughout your whole career you can be ready for some of this stuff hitting you. About 20 years ago I was sitting in one of these classes with Maurice Wilkes telling us about the future of computing, and he was probably over 90 at the time. He'd done his work in World War II, he'd worked with Turing. Everyone laughed at him coming in, this little old grey-haired man. What on earth is someone like that going to tell us about what's going on in the dot-com revolution? And Maurice Wilkes didn't talk about the dot-com revolution at all, because he thought it was all quite silly. He told us that in 20 years we'd all be carrying around a little embedded computer in our pocket, and it would be running a Java virtual machine, and it would be permanently connected to the internet through something called aorta, always on internet access. And we thought he was absolutely bonkers. This was the time of dial-up modems and so on. But Maurice Wilkes was absolutely spot on in his 20-year futurology, and that prepared us all for 20 years of our careers. So I don't claim to be as good at futurology as Maurice Wilkes, but I've done my best to talk to a bunch of people who are involved in different areas of computer science research who can give me ideas to pass on to you about what the future could look like. So this lecture is organized roughly in order of wackiness. We're going to start with what's happening in the next couple of years, maybe over the next decade, and then we're going to go more speculative until we get to about 70 millishoperas on the wackiness scale, looking at crazy things to do with physics and so on. It's lovely to see so many of you still standing for the last lecture. There's more of you left than last year, a lot more. Okay, so before we get on to the really crazy stuff, let's look at what is happening right now and is likely to continue for the next few years. In 2017, Hennessy and Patterson were given the Turing Award for their work on architecture for the development of RISC. And they gave a lecture. I'll send you a copy of the write-up of it. They gave a lecture called Computer Architecture, the New Golden Age. So a new golden age of architecture has just been declared by recent Turing Award winners. And they say this is being driven by the end of Moore's laws, however you interpret them, together with this new movement of open source hardware development. When you put these two things together, there's this huge demand for radically new ideas in computer architecture, and there is now the technology and the people who are able to work on those ideas and to deliver them. We talked about RISC-V in the last lecture. We've looked at the architecture of RISC-V, the technology of RISC-V. I wanted to talk a little more about the open source aspect and the community aspect of it today. So RISC-V is the first time that real professional computer architecture has become available for use by ordinary people to do development work on. The whole tool chain used to develop a CPU is now downloadable in about 7 seconds from GitHub. This has historically been unheard of. Those tools have only been available to a handful of elite people in Silicon Valley and a couple of other places. You have to be one of the initiated to get access to that stuff. But now everything is being made available. Anyone in any country can download this stuff in their bedroom and start working on a state-of-the-art, bleeding-edge CPU design. If you would like to get involved in this, I can't give you a full tutorial on the RISC-V ecosystem, but I'll give you a few pointers. I very much encourage you to go out and get involved in the community. So this is how you actually go about designing a chip, a real CPU. There are several levels of abstraction. They're listed here from lowest to highest. At the lowest level, you have the physical layout description. For a real ISIC chip, this is a set of masks. This is a set of effectively image files showing where the copper wires will go, where the transistors will go. For an FPGA, it's describing which logic blocks in the FPGA are being activated and connected to each other in different ways. So this is the final product of a chip design process. In the old days of the 6502, people would do their design at this level. They literally taped out the chip using black gaffer tape on a large overhead transparency, and then they photographed it and miniaturized the design. There weren't any higher level tools above that. So nowadays we have many levels of abstraction, so you don't do your design work at that level anymore. So the next level up is something called a netlist file. This is a text file, effectively, data file, containing a description of connectivities between physical components and wires. So this will say there is a transistor here or a logic gate here. Or rather, it doesn't say here in physical space, it says here in geometric space. So it tells you this transistor or this logic gate is connected to this other transistor or logic gate. And there are software tools that will take a list of connectivity in a netlist file and they will compile that into a physical layout description. Okay? If you're working with 2D chips, like historically most people have done, this is a famous NP-hard problem. You've got a whole bunch of electronic components, millions of them, even more, and they all need to connect to each other, and your task is to find the optimal routes for the copper wires to get everything connected to everything else. It's very difficult to go around everybody else. So these kinds of tools have been very closely guarded by the chip companies for many decades. It's unusual to have this stuff being made available for everybody else now. Again, you wouldn't write your design typically as a netlist. We have high levels still. You can go to a language called Verilog. Verilog is the more professional version of Logisim, the tool you've been using in the workshop. So we lose the graphical interface from Logisim. We write what looks somewhat like an XML file, somewhat like a C file. It's a text file describing, again, what is connected to what, but it gives you a higher level view than a netlist. You can create structures in Verilog. So if you create something like an adder or a half adder, you can work with blocks at that level. So you'll take a compiler that runs that to a netlist and then compile that again into your physical layout. So when I was a student, Verilog was the highest level you could go, and it was still, compared to an object-oriented language like Java or Python, it was still very low level. You were still dealing with wires and adders. What we have now from the RISC-V community is this very high-level tool called Chisel. You can see Chisel's logo uses the same font as RISC-V. It's developed as a separate project, but they're very closely linked. And it's the main tool used to develop RISC-V. And Chisel, for the first time, gives us a real modern high-level language for doing hardware design. It looks a lot like Scala, which in turn looks rather like Java, plus some ideas from the Lambda calculus and from functional programming. So it's kind of a weird mix of low-level hardware work and very high-level language abstractions. So you can learn to use Chisel. You can then download libraries for Chisel. So all the components we've talked about in the lectures, different kinds of ALUs, FPUs, control units, you can download these as text files. They're programs written in Chisel, and you put them through this series of compilers until you make a physical chip. If you want to make physical chips at home, you want to buy yourself an FPGA, you can get these for 20 quid on eBay now. Again, all this stuff is much easier to do than it used to be. It won't run as fast as a £5 million mask-making process, but it will serve you very well in your bedroom. When you're sure the thing works and you get a £5 million investor, then you can productionize it. And so RISC-V itself is being implemented by various chip designs. The best known ones are called Rocket and Boom. These are actual CPU designs made from this whole stack, putting everything together. And again, it's insane now. You can just download the entire chip design from GitHub and see a state-of-the-art CPU. This stuff used to be kept locked in a giant company's industrial research center. Now anyone can have it. Just to show you what this looks like then, here is some chisel code for an adder. I would encourage you to download this stuff, try and compile it, see how far you get. If any of you are doing Java, maybe even C++, it looks like that kind of design. So hardware design is really software now. You don't work at a chip company and dress up in a bunny suit doing things with microscopes now. You sit in a desk. A hardware company looks like a software company. Some people will do that. They're probably engineers rather than computer scientists. If you're a chip designer, this is the level you can work at now. So that chisel code will then compile into something like this. This is a corresponding piece of Verilog code. And you can see instantly by looking at it, this looks like a lower level description. There's less hierarchical structure going on here. A lot of the abstractions have got compiled down into individual wires and individual logic gates sitting in the Verilog. So it's a very exciting time. There's a kind of Linux moment happening in architecture now. Anyone can go home to their bedrooms today, download this stuff, and start working on a state-of-the-art open source RISC-V chip design. Let's look a little further into the future now. Again, this is stuff that is happening in research labs, maybe company research labs at this stage. The concept of 3D architecture has been floated around for a long time. We already have some forms of 3D printing, effectively, in a modern commercial CPU. We looked at the manufacturing process using the masks. So we put different masks on the silicon, we throw stuff through the mask, and typically we lay down a bunch of transistors on a 2D plane. All the transistors sit in one plane, and then on top of that, we now create maybe several layers of copper wires. So your traditional chip design was a purely 2D creation. If you look at the circuit for the 6502, it's all laid out on a 2D diagram, but modern technology does allow some three-dimensional aspect. This is somewhat similar to a neural network structure. You have a layer of transistors and then a bunch of wires connecting everything to everything else, but you can now shortcut some of these complex NP-hard root finding problems from the 2D plane by allowing some of the wires to go over each other, but we can only do this for a few layers, okay? So a current research area is to move away from a silicon chip to something called a silicon cube. So why should chips have to be two-dimensional? Now we have 3D printing technology, more advanced masking technology. If you look at a computer like the human brain, it is clearly a big three-dimensional chunk of stuff. So you pack a lot more computing into a physical space by going upward. You also can get gains in connectivity. Much of computing now is about getting the information from one part of the processing hardware to another. And if you're in 3D space, you have a lot more options. You can generally connect everything to everything else with an almost perfect straight line because you don't have these issues about having to route around everything in 2D. Remember, a line is only one-dimensional. So in 2 dimensions, lines can cross, but in 3 dimensions, they generally don't cross at all. This has been a dream for many decades now. Some people are claiming it is coming imminently. Here are some links to those people, an article in the book. Obviously, it has a whole bunch of engineering challenges associated with it. One of the main ones is heat. Again, we've talked about energy and heat all through the module. We are already emitting a lot of heat from a 2D chip, and as you pack things together in 3D, this is going to get almost exponentially worse. One dimension of worseness added into the mix. Again, if you look at a computer like the human brain, there's a lot of stuff in a brain that isn't doing computation. There's a lot of blood vessels, which are both transmitting energy into the compute units, the neurons, but they're also performing cooling. The brain is being cooled by the flow of blood through it. It's taking energy in and it's bringing heat back out. So equivalents of those have to be solved at the engineering level. We need new ways of making masks or mask-like processes, 3D printing processes to produce this kind of device. When we come to do design in 3 dimensions, most chip designers today have been brought up in a generation that thinks in 2 dimensions. All the tools I showed you in the chisel stack, for example, are based on this idea of a 2D net list. That's always been the challenge, to take your design and lay it out in 2 dimensions. No one yet has grown up thinking in 3D. How do we do a 3D architectural layout? The only people I can find who are really thinking about this are kids playing Minecraft. So if we have any Minecraft players here? Yeah? You know what Redstone is? Okay, so Minecraft is this virtual reality 3D game. You can create a world out of small building blocks, and there's a kind of block called Redstone which performs a simple type of computation. What we see in some of these designs, I'll try and play with video too. This is a computer called Andros 2. These are kids who've built a full church computer using Minecraft Redstone. So they've taken all the same architectural concepts that we've seen, building up logic gates, building up simple machines, microcircuits. But instead of thinking in terms of laying out in 2D, if you come from a Minecraft background, you intuitively think in 3D. If you talk to school children today, they all play this at home and they design things very naturally in 3D. So you can see here there's a whole system. There's a control unit, there's an ALU, there's a memory system. It's a fully functioning computer, able to run some simple programs. But the shape of it looks much more like, say, Babbage's engine rather than a modern 2-dimensional layout of silicon. You know, this almost looks like his parallel computing registers that we saw in the analytic engine. So just maybe there's a generation of school kids growing up now who think intuitively in terms of this kind of 3D design. Maybe those people are going to come up and they won't have all the prejudices and traditions of the 2D silicon community, and they're very naturally going to think, why not just do everything in 3 dimensions from the first place? Maybe we'll have a new generation of 3D chip designers from that. Okay, let's look a little further into the future. We have mostly been talking about electricity-based computers. We've been computing with electrons. So we started looking at semiconductors, transistors. We built logic gates from them. But if you remember from the start of the module, we also saw other attempts at computing. Computers that use mechanical systems. We saw a computer based on water. We've seen computers based on rocks, the abacus. At some point, electronic computing apparently is really going to have to run out, because we've already seen Moore's law for clock speed run out. For a long time, Moore's law for clock speed was about equivalent to Moore's law for transistor size and transistor density. We saw the two have separated over the last decade. So the Moore's law for density and size is still current, but if we project that into the future, this is a logarithmic scale, this is the size of transistors, we will see that when we get to around 2060, Moore's law for size cannot continue, because we will hit the size of a single atom. So you either have to find a way to make a transistor out of a single atom, or that's the place you give up. As you reach that stage, you also encounter the effects of quantum mechanics. These are different physical laws from Newtonian physics that make everything behave very differently. We'll talk about quantum computing later in the lecture. So this suggests that we have until probably about 2050 to find something radically different. The age of silicon is still going to last for a long time, maybe through all of our careers, but at some point, something has to change. This is an example of single atom manipulation performed by IBM, which I was hoping to have a video, but I don't. I'll just show you the screenshot. These dots are individual atoms laid out on the surface of a piece of copper by IBM researchers. So IBM's developed the technology both to move these around and put them where they want, and also to image them, to visualize them. Again, when you get to this level, you start to see the weird effects of quantum mechanics. You can see these kind of wave-like structures all around it. You can never be quite sure where an individual atom is. They start to become quite fuzzy entities. But this shows you we do have the technology for single atom manipulation and visualization now. You could almost imagine somehow moving these things around to form some kind of logic gate at the nearly atomic level. Probably get a Nobel Prize if you actually figure out how to do that. But beyond the idea of electronics and atoms and electrons altogether is this notion of optical computing. Electrons have mass. They're quite big objects compared to light, which has no mass. Light moves faster than electrons because it has no mass. It moves at the speed of light, which is the top speed that anything can go in the universe. So for several decades now, since I think 1964 was the first of these, people have been discussing how could we compute using light instead of electrons. We already transmit information in this way. We already have fiber optic cables in our networks. This is a mature technology. It's linking Europe to America's internet backbones. But actually computing with light is more difficult than transmitting information. The reason is that because electrons have mass, they interact with each other. If you shoot an electron at another atom, then they hit each other and something happens. Whereas photons will go straight through each other. So perhaps the notion of computation is somehow bound up with a basic notion in physics that things have to interact in order to compute. So what we have to do is somehow combine optical effects with some other effects. We have to have, currently there are researches into electro-optical hybrids. So remember we saw electromechanical hybrids in the age of relays before we moved to valves and transistors. It's a similar point we have now. Now, an optical computer in a lab can look something like this. Again, this is similar to the giant transistors and the mercury delay lines we saw. Typically, you will see a lab with a whole load of laser beams and lenses and prisms, and everything's positioned very carefully. But there are also people who are working on miniaturizing that. Intel will now have a opto-silicon research center. So they're trying to figure out how we, again, make that very small, fit it on a usually silicon-based chip, and enable the light to flow in certain ways, perhaps to be sensed by non-light elements, turned into electricity for short periods, and then turned back into light again. So this is an attempt at an optical transistor. You can see the three light beams. There's a switch, and the switch is going to turn on the pathway from this input to this output. So it's important to understand individual electrons flow quite slowly through copper wire. They bounce around. There's a lot of stuff in a copper wire, and an electron is constantly interacting with the atoms around it. An individual electron moves quite slowly, but the electric field, which is what's actually sending the signal, does move quite fast. So the speed of electricity, rather than the speed of an individual electron, is of the same order as the speed of light itself. So you don't get an immediate speed up just from light traveling faster than electricity. So you don't get an improvement in what we called latency last time, but you do get huge improvements in throughput. Sending an electron down a long copper wire, say to America on an undersea cable, it's very noisy because the electrons are interacting with so many atoms in the copper. It's a very noisy process. You need a lot of energy to encourage your electron to flow through there. Whereas a fiber optic cable is designed to be as transparent as possible for a photon. It will guide the path of the photon, but there's not as much stuff getting in the way of its propagation. So you get advantages in throughput rather than latency, and in much lower energy usage. There's less heat being emitted by these systems. Less energy is getting lost in the computation. So optical transistor research has been ongoing for a long time. Sometimes they think they've made a breakthrough, then it doesn't quite work out. It has a slightly sketchy reputation for making these promises several times. It's been going on since the 60s, and we still don't quite have one. But there's a special case of optical computing which has become very practical in the last few years. And this is called an optical correlator, or a 4F correlator. So this is not a general computer. You can't build a von Neumann architecture out of this. It only does one thing. It computes Fourier transform. Have you done Fourier transforms in your math class yet? Okay, so Fourier transform is a very numerical intensive unit of algorithm. It turns a signal into its component frequencies and back again. So if you're a musician, you use these in your graphic equalizer. It turns the sound signal into the peaks on your graphic EQ, and you filter the EQ by turning them up and down, and then another Fourier transform turns them back into sound in that case. Similar processes for video. It's used in all your video codecs when you're streaming YouTube, for example. So it's such a basic ingredient of certainly signal processing computation that it is worth investing in technology to make this go faster. We build so many other things on top of this particular platform. In particular, the recent wave of deep learning, neural networks research has mostly been building on GPUs. It's running something called a convolutional neural network, and the operation performed by a convolutional neural network can be set up in these terms. You can make that go faster with an optical correlator, and that's perhaps going to be the killer app of this stuff. So how does this work? If you take a laser and you shine it through one tiny little hole, you will see what is called a diffraction pattern. You will see that the thing that comes out is different to the pattern that's gone in, something like this, okay? If you then take a whole image, like this matchstick man, illuminate that with a laser, so now you have a complex image going in, and you put some lenses in the right place, or one lens in the right place, even. You can make this processing of the laser pattern give you the full Fourier transform of what went in. So as it turns out, you can place your image here at the focal length of a lens, place a detector at the other end of the lens, and if you play this image in, you will get the whole Fourier transform out at the other end in order 1 time, okay? Which is a very significant speed up for these types of application. So until very recently, this has been known for a long time, but it's not been practical for a long time. What's happened in the last few years is that technology from the mobile phone industry and from 4K screen displays, the television industry, and in particular overhead projector industries, has developed the same technology that is needed to do this. If you take what's called a spatial light modulator, it's the thing that creates the image in the projector. Actually, this isn't a projector, this is a screen. If this was a projector, it would be the same thing that is creating the color image there. So it's a very high resolution display. You shine a light through it and it makes the light project in the colors that you want. That technology can almost be taken out of those other commercial applications and plugged straight into this. If you take this display from an overhead projector and then put it on a lens here, and then take, say, the sensor from a digital camera, made with a technology like CMOS, you can actually make this work to an extent now. And it's not been a development from this research field itself, it's a consequence of those technologies being made in consumer electronics, displays and cameras. So what we can now do, almost, is take a 4K display, that's 4 million pixels, we can refresh it at 15,000 frames per second, and we can compute image Fourier transforms at that high resolution at 15,000 frames a second. And if you can shove your other kinds of data into an image, you remember what the GPU people started doing? When GPU computing first started up, they hacked it. They figured out ways to disguise their mathematical problems as image processing problems. So it's the same idea. You have to pack all your information into an image and in a form that can be Fourier transformed to do something useful. The key property of all this, again, I'm not going to go into the maths here. You'll learn this in your signal processing class, but the key property of a Fourier transform is that if you take the Fourier transform of an image like this, and then you multiply that image by another image, it's easy to multiply images together, but it effectively performs what's called a convolution in the native image domain, which is a kind of blurring. If I take a smaller image, like a little Gaussian blob, and I sweep that over here to make a blur. If you've ever done a Gaussian blur in Photoshop, this is exactly what it's doing. That process is called convolution, and it's very, very computationally intensive. Again, it's also used in audio signal processing. If you're a guitarist and you put on a graphic equalizer filter on your guitar pedal, it's running a convolution filter to change the signal. So what you can do is replace this very time-consuming process of correlation or convolution in the image domain with a very fast multiplication in the Fourier domain. So what you actually do is you build this system called the 4F filter. It's got two lenses. It's got an overhead projector style display here. It's got another overhead projector style display here, and it's got a CMOS sensor like you're getting a digital camera at the other end. So you take your input image like this. Let's say we want to blur it with one of these Gaussian filters. We're going to make that image on the overhead projector display here. We pass it through a lens. That converts it into this Fourier transform. And then we take the Fourier transform of our, what's called the kernel. That's the shape of the Gaussian blur we're doing, or the shape of the graphic equalization we want to do for the guitar signal. We light that up on this overhead projector screen, which is semi-transparent, so it multiplies with the input signal. It performs an in-place multiplication in order 1 time, and then you Fourier transform it all back again through the second lens, and you get the desired result. So to do this, say a Gaussian blur of this image on a regular computer would take a long time. If you run a Gaussian blur on Photoshop on a big image, you notice how long it takes. But here, the whole lot can be done in order 1 time. It's 2 Fourier transforms and a multiplication. So the killer app of this may be in what is called deep learning. When you do deep learning, you'll learn about neural networks in more detail later in your studies. But roughly, you're going to start with an image, and you're going to do that same kind of convolution process. You're going to make a little window of the image, maybe 30 pixels by 30 pixels, probably 32. And you're going to sweep that image across the big image, and you're going to multiply all the pixels together. It's the same kind of convolution operator as in processing a guitar signal or doing a Gaussian blur. And that's the basic operation used in what is now called deep learning, what used to be called neural networks, or convolutional neural networks. It's the same word, convolutional. So we currently do this mostly on GPUs. We buy a lot of GPUs. We do this very heavy-duty parallel computation, consuming a lot of energy, giving off a lot of heat, draining all our batteries, to try and make neural networks go fast. And it turns out that's the exact same operation that these specialist optical correlators can do in order 1 time. So there's potential for huge gains in both speed, but also in power consumption, or power consumption reduction by switching to optical here. This is what these systems actually look like in a lab when you set them up. So here's the input. This is something like the projector from the screen from an overhead projector. It goes through a lens. You have another projector screen here. This is doing the multiplication. You have another lens, and then you have a camera sensor at the other end. And it's called 4F correlator because each of these is the focal length of a lens. So the physical length of the whole thing is 4F. Okay? So this was done last year, 2018. They took an input image, these are these things called convolution kernels, they're things that are getting swept across the image. This is the kind of calculation that a deep neural network will do, and you can make the whole thing go in order 1 time using the physical system. So until yesterday, I thought this stuff was crazy research stuff, and then I spoke to Nick New at Optalysis in Wakefield, of all places, who is actually commercializing this now. So I had probably the most interesting conversation of the year so far with Nick about this. Nick did his PhD in Cambridge in this stuff back in 2001. It was a very theoretical area. He was taking the ideas from the 1960s, trying to make them go a little bit more real. But he then moved home to Wakefield, where he's from, and set this up as a commercial spin-out. He's raised about £4 million to fund it all. He's got a bunch of people working for him. They've got a little office in Silicon Valley as well now. And they've built this. They've miniaturized that whole stuff, not quite to chip level yet, but to PCIe level. So this is a product. You can nearly buy this off them now. You plug that into your PCIe slot, and you get an optical computing coprocessor to slot into your computer. It's going to be used in a similar way to how we currently use GPUs to do parallel computing. So already, they claim this thing is running around 7 times faster than the GPU version. They have implemented what's called a TensorFlow interface to it. So TensorFlow is one of the levels above OpenCL that is used for controlling GPUs. So you can almost take your GPU program and run it on the optical processor now. And it's especially interesting to us in robotics. We might put one of these on an agricultural robot here at some point, because it only draws 60 watts of power, and most of that power is just running the supporting FPGAs on the circuit rather than the lasers themselves. So we care a lot about trying to not put GPUs on robots because they're eating so much power. So Nick's currently applying some of this to problems in biology. There's a correlation problem in DNA analysis. You have 2 massive strands of DNA and you're trying to line them up, find out where the AT, Cs and Gs match with each other. That becomes a correlation problem. So they're working with the Earlham Institute over in Norwich on this stuff. There's problems in plant sciences, life sciences, and increasingly on these deep learning applications. So I'm really excited about putting one of these on an agricultural robot here in Lincoln, getting the deep neural nets on there and recognizing plants as we go around without having to put a GPU on the system or without needing a huge communications link back to base. We can reduce our power consumption doing everything optically. They reckon next year this is going to go 100 times faster than the GPU. That's when it's going to get really interesting. And they're also working on miniaturizing the whole thing down to chip size now. So they're talking to Intel about silico-optic interfacing. I just thought this was an amazing example of someone in the north of England. He has deliberately not set this up in Cambridge or in Silicon Valley like everyone else did. He reminds me a lot of William Shockley, actually. William Shockley invented the first transistor. He moved back to be near his mum in California, and the whole silicon industry grew up around him. You know, maybe we will see an optical processing industry based in Wakefield. Who knows? So, optical computing turned out to be surprisingly near commercialization. I only found out that yesterday. Thank you, Nick New, for your help with that. Let's look into even more research-based types of architecture then. DNA computing has been floating around for a couple of decades now. Does everybody know what DNA is? Could anyone draw the molecule? Okay. Roughly, DNA is the source code for your body or for a life form's body. Lots of people are currently having DNA analysis bought for them as a birthday present. You can find your family history by having your genome read now. It looks like this. It is a base 4 machine code, almost, usually written with the letters A, T, C, and G. This is the source code for you or for any life form. And it's represented in these large DNA molecules. There's a double helix of them that is very famous. And each link across the helix is one of these letters, effectively, A, T, C, or G, called a nucleotide. From a computing point of view, we think of it as a string. It's a base 4 representation. And the way this gets used is the DNA, come on, this is high school biology. The DNA sits inside the nucleus of the cell in its helix. And when we want to make stuff, we open up the DNA, so the two parts of the helix split, and something called an RNA molecule gets formed. So what happens here is the RNA is being paired with the DNA, and effectively, from a computer science point of view, it's making a copy of what was sitting on the DNA strand. And in biology, in normal biology, that RNA then comes out of the nucleus into the cell, and it then has the code for making a thing, for making a protein or a piece of the cell. That's regular biology. We now have this field called synthetic biology, which is hacking biology. It's taking that system and using it to engineer new things. What can we create using that technology? So it's now possible to create your own DNA strands surprisingly easily. If I give you a string like this and you want to print out a molecule like that, it's actually been done on a regular consumer inkjet printer, if you follow this link. These people have hacked a 4-color CMYK inkjet printer, and they've filled up the 4 ink nozzles with A's, T's, C's, and G's. And then they move the print heads around over a microarray, and they literally just print out a genome out of DNA. If you don't believe me, go and read the paper. There's the reference. I didn't believe it either until I saw the paper. So we also have technology to edit DNA, all the things that you do in your favorite text editor, like cutting things, splicing things, inserting things. There are well-established technologies that can be used to do this. Typically, you will take your DNA strand, you will make a special module called a primer, I think. The primer is designed so it binds to the exact part of the DNA that you're interested in, and then it has some kind of payload that does something. It might be cutting the DNA, it might be inserting something into the DNA. And of course, all of this is done at scale. You don't do this on one DNA molecule, you do it on a whole vat of this stuff simultaneously. And most interestingly for computer scientists, since 1993, 1993's Nobel Prize in Chemistry, we now have the ability to scale up a arbitrarily chosen piece of DNA to fill the vat. So if I give you a vat with 10 to the whatever copies of DNA, or perhaps they're all different versions of DNA, there might be one molecule somewhere in that vat that we like. It might have the solution to our optimization problem in that one molecule, but it's very hard to find it, okay? There's now this technology called PCR, polymerase chain reaction. And this works by putting a whole load of these primer molecules into the vat. So you've got 10 to the whatever different DNA strands. One of them is the one we're looking for. It's a search algorithm. We can fill the thing with a primer molecule that is designed to look for the one bit of DNA that's got the property we want. Which one's got the solution to our traveling salesperson problem encoded in it? And when the primer finds it, it performs what's called an amplification. So remember we saw this RNA producing process. This is how DNA is almost copying itself, okay? So in this case, it's getting transcribed to RNA, and the RNA is going off to make a protein, which is something different. But you can hack that and use it to assemble additional pieces of DNA. So you have these 3 steps in the PCR reaction, and these are all things that you chuck into a vat of liquid and stir them up in a biology lab. You have the first stage is going to separate the DNA strand. It's going to open up the helix. Then you put in these primers. So these are the little red molecules. They are only going to bind to the molecules that meet their desired property. So they can test, for example, if you've just solved an NP-hard problem, if this is the solution to a traveling salesperson problem. And if they do bind, then they make it copy. Okay? They trigger a copying reaction. And so this thing, it's similar to a nuclear reaction. It becomes self-sustaining. There might be billions of these molecules floating around, all with different attempts at solving a traveling salesperson's problem. As soon as one of these molecules randomly binds to one of them, it starts copying itself. And now there's 2 copies of it, and then they're going to split and make 4 copies. And before you know it, the entire vat, or a large portion of it, is all going to be full of copies to your NP-hard problem that you can then read out. So again, this sounded quite wacky until 1994, when someone actually did it. Since then, we've been scaling up. In 2004, at least, we were solving a 7-city traveling salesperson problem in this way. So has everyone seen this problem in algorithms class? Yeah? So you've got 7 cities, they all have distances between them, and your traveling salesperson starts at city 0. Their task is to visit every city and get back to where they started in the minimum distance. Okay, and it's a famous NP-hard problem. So what these guys do, this is what it looks like in the lab. This isn't computing as you know it. This is computing with lab coats and gloves and pipettes and liquid. We encode every possible solution to this problem as a different piece of DNA. We encode each city as a short chunk of DNA, and then a candidate solution, like a set of roots, is a bunch of those cities put in a sequence. It's a string explaining a route around the cities. And then you chuck that into the PCR process. We have a primer molecule which looks at a piece of DNA and says, does this piece of DNA have the property I'm interested in? Does it have a tour of the 7 cities that hits each one? And does it have a length below n? This is how you convert NP-hard problems into binary yes-no problems. You can run this several times for different lengths. And so these primers get chucked in. They bind to all the different hypothesized sequences. And sooner or later, one of them will find one that gives a positive answer to the question, and as soon as it does that, that thing starts replicating itself. This is computing with life, that the solution is set up so that it will breed until your whole vat is full of little copies of solutions to your traveling salesperson. And so you pull it out with this this is the same kind of DNA profile you see in crime scene investigation. You're testing the DNA of a criminal. You're going to look at these same kinds of patterns, and that is going to contain your solution. You can read off from there what is the optimal order of the cities to visit in your traveling salesperson problem. Okay? So again, we're used to this kind of world. We're used to zeros and ones, but we're seeing it getting encoded in base 4, put inside this double helix, and then it goes in a lab like that. This is one future of computing. We're going to come out of our bedrooms and into the lab, like real scientists in white coats. Again, this probably isn't going to become a fully generalized version of computing. You're probably not going to be watching YouTube videos based on this technology, but you might be solving difficult optimization problems like timetabling every student in a university to be in the rooms at the optimal time, or figuring out how to transfer goods across a supply line for a supermarket company across the whole country.